Hi, I'm RC Jim. Have you just gotten started with radio-controlled airplane flying? Or maybe you're considering getting into it? Well, I want to clear some of the fog with regard to some confusion that can come into things. Now, it might be that all you want to do is fly an airplane and let somebody else worry with all the technical stuff, and you go to a club and get somebody to set up things for you and off you go and fly. Hey, that's fine. Nothing wrong with that at all. If that's the case, you don't really need to watch this video. But if you want to sort of understand the stuff that's going on and you want to be able to set up things yourself, and you're feeling ignorant, when you talk to people and they're using all this terminology that you don't understand and you want to know what's what, well, then this is for you. Now, right off the bat, I'll let you know that this is all written up in a document that you can get on our website. So you can go to rcjim.com, and there's a document there that I've written up the content. And that'll be something that can be handy for you if, having watched the video, you're then trying to remember what it was that was about something. You can go to that document and find it quite quickly, and so it can be handy for that. But right now, I'd like to go through and explain some of these things for you and help you to have an understanding of what's going on. Now, related to the confusion that happens is you got all kinds of brands of different transmitters and things like that, and you just don't know what to start. Should you go with Spectrum, Futaba, FlySky, Radio Master? What should you work with and what should you use? And you'd really wonder about that. Well, we're going to help you with regard to those things. Now, each of these brands has got their own protocol. And a protocol has to do with how the signal is configured that's sent out from the transmitter to the receiver. Now, as you think about it, all of these radios here are using the 2.4 gigahertz band of radio transmission. But your garage door opener is also using that. Probably your remote on the TV is using that. This microphone that I'm recording this with is using that frequency band. And so how does the receiver know what to pick out of all those radio signals that are around that is supposed to determine what it's supposed to do? Back in the old days, you'd have a channel that is specifically assigned to that, and if anything else was on that channel, you're done for. It just had to be only you that could be, using that particular frequency. Not so anymore. There's all kinds of stuff around. So the protocol has to do with like a coding that's being used to send to the receiver to identify that this is a signal that I want you to recognize and use, and then how it comes across and what specific frequencies are being used within the band. All of that is being determined by this protocol that's going back and forth between the two. Now, each of these ones will have a different protocol, but each of those are doing a similar thing. Maybe not this Joy's way, that's more of a toy type thing, but of these serious type transmitters, they have different ways of working out what frequencies to use and how to change between them. And basically they're using multiple frequencies, they're hopping around between them to make sure that a signal gets through. But each one has their own system to do that. In some cases, that particular protocol is something that's popular enough for other people to emulate it and to provide something that does the same thing. So, for example, that NX6, that's a Spectrum transmitter. It uses a DSM-X protocol, and you can get any variety of receivers that will be compatible with that. And one good one that I use a lot of is Lemon RX, and that is a DSM-X compatible system, and so it recognizes the signal that's coming from the Spectrum radio. Or the Radio Master using a 4-in-1 module, which is duplicating what could be done with a Spectrum radio. It'll also receive that. So there's a little bit of going back and forth with some of those things. As you think about the function of the radio, there's actually two things that are going on. You've got a computer in there that's working out what to do with what happens with the position of various sticks and switches and things like that, and what all of that's supposed to mean. As it does that, it might also be altering what's happening when you move that particular control. So for example, with this particular radio, if I've got it in mode 1 with a switch up all of the way, and I move the aileron all the way to the right, it's going to have a certain position that it puts that aileron in. But if I move up to high rates by pulling that switch down and I go all the way over there, it's going to move that control a lot further. So I've got fine control in mode 1 for very small movements, very fine control to make it very precise. But if I want some extreme aerobatics, then I go up to mode 3 and whack that thing around and really get a lot of very sort of violent type maneuvers. And that's something that's a function of the computer that's in here that's determining what happens with all of these to determine what sort of signal that needs to get sent out. But then there's also a transmitter function of the radio, and that's separate from the computing function. The transmitter function just simply needs to say, okay, the computer's worked out that the aileron needs to be in this position. How do I send a signal out to the receiver to tell it to put the aileron in that position? And that is a function of the transmitter in the radio. With this particular one, it actually has 2 transmitters. I got one in this module on the back that is removable, and you could put a variety of different ones in there. So it can choose to use that for the transmitter, or there's also one right behind that inside the radio, and it can choose to use that one. So that transmitter function in the radio is working out what to do to send a signal to the receiver that can be understood and what it needs to do. With these transmitter modules, I mentioned that this one can be compatible with the receiver that works with a spectrum transmitter. That's done with a 4-in-1 module. That 4-in module actually has 4 different computer chips, and with those computer chips, it can talk to dozens of different protocols, different radio manufacturers and things like that. Not absolutely all of them, but certainly most of them, and be able to function in that particular way. Now, as you're selecting a radio system, you need to think about what you're going to be using it for. If you got a conventional set of plane that you're going to keep in sight and function with it in that particular way, then any of these radios are going to do a fine job with it. They're all 2.4 gigahertz radios. They all have line of sight sort of capability. So something, well less than a kilometer, no problem at all as long as there's nothing in the way and stuff like that. That's not to say that they're never going to have glitches. There's a variety of faults that can happen along the way, problems that can occur, but nonetheless, by and large, they're going to be reliable and functional in that line of sight. But if you're flying a drone and you're going to put on some goggles and fly it from a remote sort of spot and the drone is 20 kilometers away or something like that, you need a whole different system to be able to do something like that. So for that type of thing, you're going to need something like, say, this module I have it back on here, which is an Express ELRS system. And something like that, it's said that they can do up to 30 kilometers away in certain sort of situations, with certain sort of settings and things like that. So great for going long distances. With regard to going those long distances, you do have some systems, such as this one, operate on the 2.4 gigahertz band, but there's some other ones that operate on a 900 megahertz band, which is, well less than half of the frequency of these other systems. The lower frequency is going to tend to penetrate better through objects, and it's going to tend to go longer set of distances. However, this particular one is still operating on 2.4 gigahertz and operates quite well that way. Now, as you think about the different frequencies, that brings us to the subject of latency. That might be something that you hear of from time to time. And latency has to do with lag. It has to do with how lax the system is. You know, high latency means that there might be a lag in the signal. It might take some time for it to come through. That might only be a half a second or something. It might be less than that. But nonetheless, not as quick a response as what you'd get with a low latency system. So latency, think of latency, lag, lax, slow. Low latency means faster, quicker, more response. Before we go any further with that, as you think about this Express LRS module on the back here, that has to do with the transmitter module. So as you think about this radio using ELRS, that is with regard to the transmission. But in terms of the computing that we discussed going on here, this is a Edge TX system. Edge TX has to do with the computing system. ELRS, or the 4-in-1, has to do with the transmission of the signal. As you think about the range of a signal, and as you think about potential glitches that come into the process, there are a variety of things that will reduce the range of a radio signal. If I've got the radio right next to me, and I've got the plane flying behind me someplace, my own body could get in the way. If I've got another flyer in front of me, his body could get in the way. If I fly behind a tree, the tree can get in the way. You know, so you can have various things like that that are a problem. Components of the plane can get in the way. If I've got a great big battery and that's blocking the signal from the antennas on the plane, that might be a problem. Or other electronic components in the airplane. Those things can potentially block a signal. The orientation of the antenna will make a difference. If the antennas are both parallel to each other, this antenna versus the receiver antenna, they're both pointed in the same direction and they're parallel, then that is going to be the best in terms of receiving a signal, especially if it's right perpendicular to the radio. If they're off this way, that's still pretty good, but the power of the signal coming from the transmitter is going to be the greatest side onto it, and it's going to be the weakest as far as the end-on signal is concerned. So if I have either the transmitter antenna pointed straight at the plane, or the plane's antennas are both pointed straight at the transmitter, either one of those are not going to be very good. So because of that, we typically mount the antennas in the airplane to be perpendicular to each other, and if possible at some distance to each other, so that if something like the battery is blocking the signal, that might be true with one but not with both, and being perpendicular to each other, if one is pointed straight at the transmitter, the other one is perpendicular to the transmitter. Of course, with regard to the antenna on the transmitter itself, some, like the Spectrum, will actually have two antennas in it, one horizontal and one inside this end thing here. Crazy thing is that a lot of people will fly with it like this, with this antenna here pointed straight at the plane, and that's kind of crazy, not doing much of anything. And in actual fact, as you think about it, when you're flying an airplane, typically you're going to be looking at the airplane, and very naturally with this antenna either being vertical or horizontal off to the side, it's generally got a good sort of signal going to the airplane. So I've done some testing, and a lot depends on how you have your plane set up, but I generally have mine vertical, and I point it up so that it's square onto the plane when I'm looking at it. Now, the radio transmitter that you hold in your hand is what has all of the switches and sticks and things like that for controlling the airplane. This one is mode 2, which means that the right stick acts just like a joystick. So pull it back to go up, push forward to go down, bank to the left, bank to the right, just as if you were flying an old-time airplane that has a stick for control. You got throttle on this side and rudder going back and forth. So you then have all of these switches that can be set up to do different things. So I've got flight modes to make more aggressive flying versus more easy to control sort of flying. I've got flaps and two different positions of down flaps. landing gear over here, whether the stability is on or off over there, the amount of stability control that's being put in here. I have some switches over here to turn on and off certain special functions. So you've got all of that type of thing. Arm the throttle over here, reset the timer. So all of these things do different stuff. Okay, so the transmitter that you hold, it's got a transmitter module in it that's going to send a signal, and that's going to be received by a receiver. Some receivers have one antenna, some have two antennas, and you can even get a little satellite module that you can plug into the receiver, which goes into there. And with that, you can then have 4 antennas. But anyway, the signal that's going to the receiver is going to be according to whatever protocol is being used, you know, whether it's the DSMX or ELRS or whatever it might be. The receiver picks that up, and when the receiver goes to send a signal, if it's this type of receiver, it's using PWM, pulse width modulation. And with pulse width modulation, as it sends a signal to a servo that is going to rotate and move their flight controls, so it sends it there, every little segment of time, and very tiny segments of time, it's going to send a pulse of electricity. And how long of time that pulse lasts for determines the position of the servo. Now let me just demonstrate that. This is a meter that, if you're flying electric planes, you're definitely going to have one of these guys. You really need it. I can plug in power here. If you're just measuring voltage, you just simply plug in the power to whichever connector you have, and it tells you what the voltage is. But in this particular case, I'm going to use it to control the servo. So I'm going to hold in the button there. And you can see we got a number there, and it says microseconds. So that signal is the number of microseconds for each one of those pulses. So it goes all the way from 1,000 up to 2,000. So 1,000 microsecond long pulses versus 2,000 microsecond long pulses, all happening on a regular basis of a very, very short period of time, because we are talking about microseconds. So when you have a servo being controlled by that, and of course this is just for testing, you don't have this guy in the plane, you use this for setting things up and all. But when you've got that servo in there, depending on how many microseconds it is, it changes the position of the servo. So 2,000, it's all that way. 1,000, it's all that way. And you got pretty well an infinite, you know, for practical purposes. It's actually tiny little steps. It's a stepper motor in there. But nonetheless, very fine control going from one extreme to the other extreme. So that's what your receiver is doing. It's generating that same sort of signal, such that when you hook up your receiver to your servo, it's going to send a signal out to that servo, and it's going to control that servo with the control on the transmitter. Now there are times that you might need more than one servo to complete one particular thing that you're doing. So let's say, for example, you've got flaps on your airplane. You've got a flap on each wing. You might have one servo for each of those flaps, and they both need to do the same thing. So for that, you might have a Y harness where one piece plugs into here and then it splits into two, one going to one servo and one going to the other servo, with the two doing the same thing. Or you might have these plugged into separate channels and then use the computing function of the radio to say what each one of those channels needs to do. Now let's think about some of the different types of receivers that you might have. This is just a basic 7-channel receiver. It's got the ability to add the satellite receiver to it to give you 2 extra antennas. And it's got the PWM outputs out here. You can get the same thing with a stabilization. And with a stabilization, it stabilizes on all three axes. And what happens if your plane is going along and a gust of wind sends it, off to the side or whatever, and it wasn't a control input that did that, then the accelerometers inside this sense that, and they will apply the appropriate controls to bring it back to where it was. You've got the ability to adjust how much is being done for each of those three axes, and you can do that on the receiver itself, and overall you can do that on the transmitter. In fact, even individually you can do it on the transmitter with certain functions. One further thought about a stabilized receiver. With ones like with Lemon RX, it's just doing stabilization. And of course, for most of us, that's all we want anyway. Just correction for the wind gusts and things like that to just make it a little bit steadier when the wind is, gusting around and stuff like that. With Spectrum, as you get into their receivers, they will have an option that goes beyond simple stabilization, and it will have a safe mode. And when you flick it into the safe mode, what happens with that is that if you're in some strange position, half upside down or whatever, the plane will automatically bring itself to straight and level flight. If you've got the throttle up, it'll slightly climb. If you got the throttle down, it'll slightly descend. But straight and level. Something like that, you get in a situation that you can't handle, you flick the switch into the stabilized mode, it brings it around straight, but then what you really need to do is turn it back off of that safe mode so that you can fly it normally to bring it back. I've heard of some people that have left it in the safe mode and they're trying to turn the plane to bring it back, and the thing just doesn't want to hardly turn. It's just such a slow turn. It's taken a country mile to get it around the corner, and that's because they left it in the safe mode. Safe mode isn't designed for that. It's designed for recovery from some catastrophe that you can't control. Myself, I find that rather useless in that by the time you think about flicking the switch and all of that, it's too late. It's already in the ground. To me, I just use the stabilization. But anyway, that is something that you can get with the Spectrum systems. And just keep in mind that you're going to pay a lot of extra money to go with Spectrum as compared to something like Lemon RX. Okay, so that's a stabilized receiver. And again, this is 7 channels. You can go up in the number of channels and get ones that have more, or you can have ones that have less. This is a 10-channel receiver, and so you've got PWM outputs on both ends of it. And with this one, you also have the ability to add in a second battery. You got BEC1 and BEC2. And so what's going to happen is it's going to basically be using the one battery, and most likely that'll just be coming in through the throttle from your BEC on the ESC, all those nice little terms. So most likely power is going to be coming in there, but you can have a second battery plugged into the other side, and if for some reason the power fails on this one will take over as a safety measure on that. And again, you've got the ability to plug in a satellite receiver. With all of these Lemon receivers and many other receivers have a similar set of things that are available. You have telemetry. And with telemetry, well, actually, with those two, there you've got telemetry. This basic one right here doesn't have the telemetry. But with a telemetry receiver, you can do a variety of things. First off, it's going to send you back information about the plane. With Lemon, it'll actually give you the altitude. It's got a little barometer in there that it uses to measure the altitude. It will tell you the signal strength, both the signal strength received by the receiver as well as you'll have the signal strength from the transmitter that's being, how strong the signal is that's coming back for the telemetry. That'll be there. But if you have a little voltage probe like this, you can plug this little guy in there into the telemetry port. This little guy can plug into the positive lead on your connector here in the battery. This is called a balance port. And with a balance port, each one of these wires is connected between each of the cells. So you can imagine a whole bunch of cells in line. Between each cell there's a wire hooked on, and that's each of these here. And that allows your battery charger to make sure that each of the cells are properly charged and one isn't hogging all of the power or whatever, which could cause some significant problems. So this little telemetry probe here, you can plug this into your balance connection and plug it into your telemetry receiver, into the telemetry port up there. And then it will report the battery voltage back to your transmitter, and you can set up alarms and things like that to say you got low battery voltage. And also in your flight log, it'll be showing the battery voltage. So alternately, instead of having to plug this into your battery and remembering to do that and not having it come loose accidentally and whatever, you can actually wire one of those onto your BEC. So with this, it's the same thing. I don't have this one hooked up, but with this one, that will be eventually soldered to one of these guys with that connector on the end of it. And that is giving the sample, again, of the total voltage. You got the total voltage on this connector. That's the one that's going to your directly to your battery. Another way to do it is that they have these little guys that can plug in series. And so we've got your ESC there. You just simply plug this into the ESC, and then you plug your battery into that end of it there. And as you do that, you're getting the voltage, but you also have an ammeter in here that's measuring the current. And with voltage and current, you've got watts, and watts over time will give you watt hours. And so it gives you all kinds of additional information about what's going on. How much power you've actually used, based on how much capacity you had at the beginning, how much of that capacity has been used, and how far you have to go and things like that. So those can be very handy as well. And again, this just plugs into the telemetry port and it gives you all that information. So let's back up a little bit now and just think about these different components and precisely what is going on. Now, if we're looking at something that's like a spectrum system, a DSMX system, it's going to, and this would be commonly true with most of your line of sight systems for receivers and transmitters. When you have that type of system, the receiver needs to be bound to the transmitter. Keep in mind that out there you got all kinds of garbage out there in the 2.4 gigahertz radio spectrum. And you now need to somehow for this receiver to pick out from all of that stuff that's out there in the radio frequencies as to what's coming from the transmitter that's supposed to be controlling it. So what you do is you bind the receiver to the transmitter. You can do that one of two ways. Most receivers will have a bind button, and so you can power up the receiver, hold down the bind button, it'll start flashing rapidly, go to your transmitter, press the bind on the transmitter, and the two will link up. Alternately, you can use a bind plug, and the bind plug will have a particular place to go, and on this one, it's the very end one, where it says A2/B. The B is for bind. And this thing is just simply shorting out the signal with the ground, just earthing the signal thing, so it really makes no difference which way it goes in there. Just connecting the top connector to the bottom connector. And with that in there, after you put that in there, you put the power on it, it'll start flashing rapidly. You press bind on the transmitter, and then that's bound. And after that's done, then you, after taking the power off, you remove the plug, and it's all bound and connected up together. So you have a transmitter that's bound to a receiver. The receiver has got servos that are plugged into the various ports where they need to go. In turn, the receiver needs to have power. Now, if you had a nitroplane, glow fuel, or gasoline-powered combustion engine, with something like that, you need to power this separately. So you might have a battery similar to what I use with that tester over there that is just dedicated to go to this, and this is NiCads that are rechargeable. So that's the right voltage, and so I could just plug it in there. Alternately, I could use a small battery, like, say, something like this little guy here, and this one is 7.4 volts, and this really wants 5 volts. So what I would do is I would use a battery elimination circuit, UBEC thing that is similar to what's in this here, but anyway, it's something that reduces the voltage down to the 5 volts, and I plug this into that and plug that into there and have the power that I need for that. But that same UBEC, that battery elimination circuit, is built into the power controller for an electric motor. So if I had a situation where I've got a ESC, an electronic speed control, that's controlling an electric motor, most likely that ESC is going to have a UBEC or BEC, battery elimination circuit. With this battery elimination circuit, it can, right when it plugs into the throttle position on there, because this control, this is going to have the signal that goes to the ESC to tell it how fast the throttle needs to go. But this in turn is going to provide power to this receiver. So it can be doing two things, sending the signal to control a motor and receiving power back. And that's going to give it that 5 volts that it needs in this particular case. There are higher voltage ones that can be used for larger planes that need more power to move controls, but most of them will be down there in that 5 volt range. Okay, so that gives us power to the receiver, and the receiver is hooked up to the servo, so it's able to control those. The receiver is able to give a signal to the ESC as to how fast the motor needs to go. This, of course, is getting power from the battery. And in this particular case, it tells you right on there it's good for anywhere from a 3 to a 6S battery. So anything from this little guy up to that big guy, either one is going to work. Just a question of how much voltage is going to get through the motor. And basically, the lower voltages going to the motor are going to have it spinning slower, and the higher voltage of the motor are going to have it spinning faster. And that's actually what that kV rating is on a motor, where this says kV 450. That 450 is saying it delivers 450 RPM for each volt that's delivered to it. So you give it 1 volt, you get 450 RPM. You give it 10 volts, you get 4,500 RPM. And as you think about these batteries, this one is 11.1 volts for the nominal voltage. This one is 22.2 volts, double, because it's 6 cells and compared to 3. And so accordingly, you're going to spin it a lot faster with something like that. But each motor will have an appropriate amount of power that it receives, and you look up those details on that to make sure you've got the right one. So you have an ESC that is controlling the motor. You got 3 leads there, and that's not actually properly 3-phase electricity. It's not like a 220 volt 3-phase motor. It's actually sending pulses in sequence, and those pulses going in sequence are going to energize the coils in here, either going one direction or going the other direction, to make this motor spin. And the ESC is determining how much power to give each one of those and how fast to make them go and that type of thing based on the signal that it's received from the receiver. Now that system there is the PWM system, pulse width modulation system, with something like this. But it's also possible to get a receiver that that uses a serial signal. And with a serial signal, the idea is instead of having a separate connector for each of the servos, you've got one connector that goes out and it plugs into the first one, and then a lead goes from that one to the next one, and it goes from that one to the next one. It's daisy chained all around to cover everything, and it means you only need one wire going through the plane to all of these things, as compared to, imagine a 10-channel PWM receiver such as this, where you've got 5 plugged into here, you've got 5 plugged into there, and these wires are going all over the place. It can be a bit messy. And of course, some planes go beyond the 10 channels, So that type of thing can be used. They're very popular with the drones, and the main reason is that with this serial signal, that little board there, that little tiny thing, is the equivalent of one of these. And keep in mind, one of these, the bulk of it is just, working out, connecting that little circuit board that's in the bottom of it with, all of these connectors going across there. So this I think this one might just be 4 channels, but nonetheless, they're very, very small. And it sends a serial signal to either a controller that is then hooked up to all of the various things that are being controlled, or it can be connected to individual servos that are designed for that type of system where they're all daisy chained together. So that's another type of thing that can be used. I might mention with this serial connection here, 2 common protocols that are used with that are iBus and SBus. Those are 2 different things, but they do the same type of thing. So similar to other protocols for other things, those are protocols for serial connections to servos and radio-controlled systems, iBus and SBus. Thank you for watching. I trust that this has been helpful to you. Now, this is just the first in a series of 3 videos where I go through the basics of radio control and try to clear the fog. So you'll want to look at that next one. There's a link over here. And with that, we're going to be looking at these different transmitters and why you might want to choose one versus another. After that, there'll be a 3rd video where I talk about the terminology, some of the abbreviations and terms that are used in our hobby. So those things I think you'll find to be helpful as well. So for those, there's a link over here. Follow that. And if you haven't done so already, well, hey, subscribe. Keep all of these things handy. There's an awful lot on our channel, and you'll find it helpful. I'm RC Jim signing off. You have a great day.